Hi, this is Bharat Durugojo. Today we're gonna explain the solution for the convolutional neural networks. So in this assignment, we're gonna use the MNIST dataset. So for this, we're gonna import some libraries and built-in functions. So first, we're gonna import the num value, and we're gonna import the matplot library as a plotting function. So we're gonna use the plotting function for the coding and for the graph. So we are importing the keras from the TensorFlow. So we're gonna import the datasets, MNIST datasets from the keras datasets. So and we're gonna import the models of sequential. So and we're gonna import the layers of dense and dropout, flatten and convert 2D and max pooling 2D. These are the layers we're gonna import from the keras layers. So as shown below from the exercise one, the first we're gonna load the data sets and we're gonna examine them. So here we are using MNIST load data function. So about this function, it is automatically split the data into training set and test set. So the divided training set and test set is gonna divided into X and Y for the training set and test set. So and these divided training set and test set, we're gonna in dimensions of these variables. So and after that, these creates necessary variables and values. So here for this, we're gonna assign epochs for 1 and 10 for the num classes. Here we're gonna take 0 to 9, and 0 to 9 is considered as 10. So and batch size is assigned as 128. So here we're gonna write the code for these following. So for the dimensions of the image, we're gonna assign the 28 for the image row and 28 for the image column, and we're gonna specify the input shape, exact shape. And here we gonna assign xtrain as a reshape for the assign as image row and column, and for the size is 1, and same as the test function. We're gonna reshape it, and we're gonna put image rows and columns and 1. So and printing the input shape. So here we are using MNIST load data for the training set and test set, and printing all the train shape and test shape for the X and Y values. And also, as I've already said, we're gonna take epochs as 1 and 10 as a num classes and 128 as a batch size. So after printing all these values, printing the code, we are getting the train shape as 60,000 and 2828. So as the test shape will be 10,000, 10,000 parameters, and the size is 28 and 28. And here the train shape. So for the train shape of Y, we are getting only 60,000 for the labels, and Y test shape is 10,000. So and after that, we're gonna specify the dimensions of the image as a 28 and 28, as I've already said. After printing all this input shape for this code, we are getting at 28, 28 and 1. As I've already said, the 28 is a image row and 28 is a image column. So and 1 will be assigned for the output. So and after that, for the visualization of this image, we can in this training set we use plotting function. Here we are taking 4 into 4. As 4 into 4, it will be 16. We're gonna assign as 16 images here, labels 1, 2, 3 and 4, 4, 4, 16. So here we're gonna, for the image size, we are taking a 10, 10 and 11, 10, 11. So the dotted per inches is 80. For this, we're gonna for this figures axis, we're gonna use enumerate. As I've already said, we're gonna, so here we gonna use num dot squeeze of for the xtrain, and cmap is the color of the is gray, and we're gonna title it as uh, f label for the y train. So here for the label 5041 and all these things, these are the MNIST digits datasets. So and after that, we for these pixel values, we're gonna normalize the X-train and X-trace of zero, of the size 0, and the range, the size 0 to 1, and the range will be 0 to 1. So we're gonna convert the Y-train and Y-test to a matrix or for to a binary values. So for this, we're gonna use the built-in function kernels, the utilist, and that will be useful for the categorical. So for this, we're gonna use the visualize the sample images. For this one, we're gonna we are using a plotting function, the subplot, as same as 4 into 4 figure size, same 10 into 11, dotted DPI will be 80. And for here we are using emirate for the figure of for the axis, and we're gonna name it as, for the label we're gonna name that the title will be f label as a Y train, and after that we're gonna normalize the input, and here we are using x train as type and float 32. These will be as a copy of an array for this, for the specified type. So here we are using for the x test, we are using a extra x underscore test dot a as type for the float 32. So for the x train, we gonna divide by 255, and for the x test we're gonna divide by 255, same as that. So after this code, we're gonna convert the class vector for we're gonna convert the vectors to a binary matrix. So here for the label train, for the Y train, we're gonna use the utilities to categorical. So Y train and for the num classes, and same as Y. So for the output, we're getting 5041 and 9213 143 13617. So after this data set, after finishing the processing of the data set, we're gonna build a CNN. So for this, we're gonna initialize this key sequential model, writing a code using the model function. Uh, sorry, the model will be assigned as a sequential function. So here we are using almost 6 layers for this. For adding a model, here we are using a model dot add function. So we're gonna add the first layer, second layer, third layer, fourth and fifth, sixth. We're gonna add the in the sequential order, like a architectural in the organized manner. So here for the first layer, we are using a conventional layer with 32 filters, and the kernel will be 3 by 3. So the activation function is ReLU. So this will be double for the second layer. The conventional layer will be double, and the kernel size will be same as first one, and the activation function will be same as first one. So for the third one, we are using max pooling function with pooling layer. The pooling size will be 2 by 2, and after the third layer, we're gonna add the dropout for the ratio of 0.25, and for the fourth layer, we're gonna use in the flat layer. uh, and after the fourth layer, we're gonna come to fifth layer. Here we are using a dense layer with 128 nodes, and the activation as an activation function is ReLU. So and after the third function, as we have already said, the dropout, we had used dropout with a ratio of 0.25. We're gonna same add the dropout of 0.25 for after the fifth layer, and after that, the sixth layer, we're gonna use the dense layer with the number of classes, and activation with the activation function will be softmax. And after this layers coding, after these layers, all these layers, we're gonna use the model summary. Uh, all this will be checked and built in a CNN. So for this, we're gonna use the references of convo 2D and dense and flatten and the dropout. These are the layers. So which gonna use. So for this we're gonna design a model architecture model. So here I've already said the model will be assigned as a sequential function. First, we're gonna add the convo 2D with the filters 32 and kernel with 3 by 3 size, and activation is 3 low, and input shape is as I've already said. And after that, we're gonna add the convo 64, which is double and 3 by 3 kernel size, and the activation is low. After this is the second layer and this is third layer. So here we are using a max pooling. We are using a pool size of 2 by 2. So after the third layer, we have already said 0.25 is add by dropout. So we are adding a dropout of 0.2 ratio, and the fourth layer is flatten function. So the dense layer is 128, and the activation function is RELU. So, and after the face layer, we're gonna again add the dropout, the ratio of 0.25, and the sixth layer will be dense, and here we are using a num classes, and the activation function is for softmax, and all the here after writing the code, we're gonna use the model.summary function for the printing. So after printing model this summary, the all this code, we are getting output shape of first layer will be none. The first will be the filters will be none, and the 26, 26, and 32 is the size. And here we are getting a 320 parameters. So and on the second, for the second one, we are getting 24, 24, 64, and by multiplying these and this value, we are getting this value 18,496. And for the third layer, we are getting the same, and the parameters is 0. These are the fourth layer. This we're gonna add the 0.25 ratio for the dropout. So the same as the parameters will be 0, and for the fourth layer, we are getting a 0 parameters. For the dense function here, we are getting at 128 the output shape, and after multiplying the fourth layer and fifth layer, we are getting a parameters of 1 million. So it's like 10 lakhs, 11 lakhs 79,776 parameters. So after the after the fifth layer, we are again adding a ratio of dropout 0.25, and we are getting 0 parameters. And here for the sixth layer, we are using the dense function as a number of classes, and in the num classes, here we are getting a 10 of the shape, and here we are getting a 1290 parameters, and the total parameters is almost 11 lakhs 99,882. So here the trainable parameters are 11, are almost the same number as the total one. There are none for the non-trainable parameters. And after this code, we're gonna train the CNN which we built. So for this, we're gonna compile the total model. So here we are using a loss to kernels dot losses for the categorical Carson trophy. So here we are using a matrix for the accuracy, and here we are using optimizer to kernels. Here we are using kernels.optimize.atom function to train the model. And first we're gonna train the model and report all these values for the code which we have printed, and the values which we got in the output. We're gonna report the values as a result. So for this, we're gonna take the references from the compile and fit methods. So here we are, so in the model training, so first we're gonna take the compile function, the model.compile function. Here, as exercise after building this one, we are using the loss to kernel's loss, the categorical. Here we are using a loss optimizer and matrices for this compile function as a compile function. So for the model dot fit, we're gonna use train x and y train, x train and y train. So the batch size will be, and batch size will be which and batch size epochs and verbals will be one, and validation data set is for the x test and y set. So for this, we are assigning the model dot value x test and y set verbals will be 0, will be assigned to score. So after printing the score, test accuracy. So we are getting a 469 by 469. So and the test accuracy is 0.9842 and all these decimal values. And here we got a loss of 0.1872. The accuracy will be 0.9428. The variable loss will be 0.0453, and the variable's accuracy is 0.42. And the variable accuracy and the test accuracy is almost same. Okay, for this we have trained the CNN and we have successfully completed this one. So after that, say we have to save the train model for the for the future use, or we may use the train function from the others also. And after that, uh, we're gonna save the train model and train the load it again, and we may test it again for the set again. So after that, we're gonna load the model and save it for the references. So, and after saving the train model for the future use, we may use this in the future and load it and test also. So for this saving, we're gonna save it for the writing the code like model dot save in function, right? Model underscore my underscore model for the saving for the future use. So to load the model, we're gonna write the code as model kernels dot model dot load underscore model for the my model. We're gonna, this is the type of the name of the uh, function. So it's not a function, it's a code. So for the loading session, for the loading, we're gonna write this code, and for the applying, or we're gonna for the future use, we're gonna apply this model. So after printing this value, and we are getting the test accuracy is almost 98.42%. So here's my explanation. Thank you.